Hello everyone, welcome to this lecture video tutorial in the mathematics of the modern world. Enjoy learning. Hello everyone, in this lecture video we will be discussing chapter 5 entitled Apportionment and Voting. In this lecture I am going to divide this lecture into three parts. The first part is we will be talking about apportionment. The second part we will be talking about voting, and finally the third part we will be discussing about weighted voting system. Okay, so for the first part, as you can see here, this was uploaded in your Google Classroom. This is your module. So the student are expected to understand the definition of the apportionment, and we will be discussing methods of apportionment, and finally this is the first one, and finally the third one is to explain the fairness in apportionment. So but the method that we will be discussing in this lecture will be this one, Hamilton. I know you are familiar with this Hamilton plan or method. Okay, the second one is the Jefferson plan. Okay, Jefferson plan or method. The third one is the Webster plan or method, and finally the last one is the Huntington-Hill method. Okay, so these are the four methods that we will be discussing in this lecture. Okay, so for the first definition, as you can see here, what is apportionment? So as you can see here, apportionment is a method of dividing a whole into various parts. Before we go forward, let's look into the verb form of the word apportionment here in this definition. So why? Because for me, there's something that I have to elaborate more of this definition. Okay, this is not just like dividing something, okay, into various parts. There's an important word here, especially this one. Okay, there are two definition that I'm going to elaborate here. So the first one is when you are going to apportion, meaning to say you are to divide and share out according to a plan. There must be a plan. Okay, that's why we have the methods that I'm going to discuss are the four methods that we discussed earlier. Okay, when you divide something, it must be according to a plan. Okay, and there's another word here like this one, proportionate. This one here, it must be a proportionate division. Okay, so as you can see here, when you are going to apportion, it should be that the division must be proportionate. It's just like when you divide something, the the proper way of distribution of something is it should be proportionate. So for example, if you have 500 laptops, okay, if you have 500 laptops, and then you are going to distribute that laptops into a school, okay, for example, there are four schools, okay. For example, we have the CMU, the BSU, Philippine Computer College, and maybe MSU IIT. Okay, so if you are going to distribute 500 laptops into that 4 schools, maybe you would think that uh, 500 should be divided by 4, right? So uh, is that a method of dividing a whole into various part proper? Is that a correct one? So just ask yourself. Okay, so it must be proportion. Why must the division must be in proportion? This is because it may be that, for example, there's a school here. Example, we have CMU, and then BSU, and then PCC, and then we have MSU IIT. Okay, IIT. So for example, there are only let's say uh, 50 teachers here, and this one we have 30 teachers here, and PCC we have 5 teachers here, and MSU IIT we have, let's say for example, there are 150 teachers here. Okay, and there are 500 laptops. Okay, and the Department of Education wants to distribute these laptops to these 4 schools or university. Okay, just imagine like that. So are you going to divide 500, since there are divide 500 divided by 4, since there are only 4 schools, and then you would say uh, what is 500 divided by 4? Okay, so it's a 125 laptops. So meaning to say this 125 laptops will be distributed to these 4 universities or schools. So there are 125 laptops here, 125 laptops here, 125 laptops here, and also for this one. Okay, is that a correct way of distributing 125 laptops to the no, not 125, 500 laptops to the schools here? So just ask yourself. So as you have noticed, if you are going to divide it this way, then notice that the PCC, let's have this another color here, only has 5 teachers. Okay, there are only 5 teachers here. So let's try to teachers here. Okay, teachers. And imagine that if you have 125 laptops and there are 5 teachers, so what will happen to MSU IT? Okay, or for example, let's erase this one and change this to, let's change this one to 200. Okay, 200 teachers. So would that be fair to this university here, that they will be receiving for 125 laptops only, and there are 200 teachers? Okay, so when you are going to apportion something, it must be proportionate division or proportionate distribution. Okay, please do remember that. Okay, so I hope now that you have a grasp of the word, this definition here, definition of the apportionment. This is not just like dividing something. The division must be proportionate. And one last example here is, this is very clear. Recently we witnessed the election of the United States. I think last November 2020. And I have here, as you can see in the screen, this is the US map. Okay, so this is the United States map. And ask yourself, how many states are there in the US map? Okay, I've read uh, in the literature, it says there that there are uh, 50 states. Others have 53 states. I don't know the latest. So suppose that there are 50 states. Okay, so let's have one here. there are, let's say there are 50 states. Okay, so let's try this color red here. Okay, 50 states. Okay, 50 states. So, and how many representatives are there in the election? Okay, so I've read also that there are 435 house representatives. Okay, representatives. Okay, there are 435. Okay, so imagine, suppose that there are 50 states and there are 435 house representatives. So how are you going to distribute the 435 representatives to 50 states? So maybe you would ask yourself, the usual way is you are going to divide the 435 by, let's say, 50. Okay, so the answer would be, let's say I have a calculator here. So 435 divided by 50. Okay, so the answer is 8.7. Okay, so 8.7. Okay, so uh, we know that there's no person that will have zero point 0.7 or something. So let's round this to 8. Okay, let's round this to 8. Okay, to 8 person representatives. Okay, representatives. Okay, so there are 8 representatives. So as you would analyze this scenario is that each of these states, Texas, we have New Mexico, Montana, and what are the other states are Florida, and so on and so forth. So each of these states will receive 8 representatives. So first, that would be your analogy. But remember that Texas is much bigger state than what's this one? This one here. This one here. This one. Okay. I think this is Connecticut something. Connecticut. So let's say this is Connecticut. Okay. This one here. So this is a small state, and this one here, Texas, is a big state, and there are many uh, people here than this state here. So is it fair that there are only 8 representatives to be put here than this one? Okay, so just analyze the situation. Okay, but as you can see, I've searched it in the internet here. I guess I am correct. We have 50 states. It says here that there are 435, as you can see here, representatives since 1913, and it was reapportioned in 1929. And as you can see in the history, in 1959 to 1962, there are 437 because Alaska was added, and also Hawaii. Okay. Anyway, let's have an example where we use the 435 representatives and 50 states. And as you can see here, there are, I guess, more than 50. We have 53 something here. Okay, 53. So anyway, uh, what I am going to show you here is that I am correct with the House of Representatives. There are 425 since January 3, 2013. And lately here, I've searched this one. This is the allocation. You can find it in this website, britannica.com. The allocation of the states, no, not the states, the representatives, 435 representatives. So for California, we have 53, Alabama, we have 7, Alaska 1, Arizona, and so on and so forth. I guess the biggest one is California. Okay, as you can see here. And where are the others? We have Texas here, 36. Okay, so where's the Connecticut? Something Connecticut. We have 5. Okay, representatives. And as you have noticed here at the bottom, we have 435 representatives. Okay, so what method do they use lately? Okay, is it Hamilton, is it Jefferson, Webster, or Huntington-Hill apportionment method? Okay, so maybe you have to search for that. Okay, so as you can see, as I've discussed earlier, you cannot distribute 8 representatives equally. Okay, because there are states that have more people. Okay, so I believe that you are now able to uh, what they call this one, comprehend or understand the definition of the word apportionment. Okay, it must be that the division must be proportionate. When you are going to distribute something, it must be proportionate. Okay, so let's try now to discuss the first method or plan, which is the Hamilton plan. And I know that you already read this remark here. This is something like an a history of uh, of apportionment, uh, and this was the first apportionment that was used was Hamilton and Jefferson plan, okay, or method. Okay, so you've read this and try to understand. It is connected with the discussion that I've discussed in the illustration before. Okay, so these are the methods. Okay, in the uploaded module, um, it says there that there are only 3 methods. Okay, I guess it was not mentioned there, the Webster method. Okay, and there's something also a problem with the Huntington Hill method that was uh, given to you in the Google Classroom. Okay, so anyway, since you've listened to this lecture, you will be able to understand the Huntington Hill apportionment method maybe later. Okay, so don't forget that I am going to discuss 4 methods. Okay, so for the first method or plan, we have the Hamilton plan. So this one here, and what are the steps in order to execute this plan? Okay, so first you are going to determine the standard divisor. Okay, so get the standard divisor first, and then after that get the standard quota. Okay, so how are you going to get the standard divisor? So all you have to do is to get the total population. Okay, get the total population and determine the number of people to apportion. Okay, divided by that one. So just like the example before, we have 500 laptops and there are um, uh, what do you call this one? No, not the 500 laptops. The 500 laptops are the something like the number of people to apportion. Okay, the total population is the population, this one here. So you have to add the 50 teachers, 35, and 200 teachers. Okay, so that would be the total population, and the 500 laptops is the what they call this one, the number of people to apportion. So as you have noticed, laptop is not a person. Okay, so by the way, the denominator is not limited only to the number of people. There are situations now that are used which is not limited only to the number of people. Okay, so I guess I am going to write it here before I am going to proceed to the discussion of the Hamilton plan. Okay, so I'm going to pause it here and then write the main idea here. Okay, this denominator. Okay, so I have written here as a comments with regards to the denominator, this one here, the number of people to apportion. This is not limited to the number of people to apportion only. It can be extended to situations like for example, the example that we had uh, before, like the number of laptops to be distributed to the number of teachers. Okay, so I write here a comment, or I don't know if the word is right, but anyway, today apportionment, okay, is not limited, it's not only applied to population. As you can see here in the denominator, maybe you would ask yourself that it should be a number of people. Okay, so population of people, but rather it can be applied to situations like this one, the number of math classes offered at a college, or the number of fire stations in a city. Okay, so let's try to elaborate this one. Let's try this one, letter A, this one here. Let's for example, number of classes, this one here is your denominator. Okay, and then this one here at the college, maybe the number of students. Okay, for example, we have CAS, the College of Arts and Sciences, and suppose there are how many departments? Maybe we have math department, physics department, let's say English department, and we have history department. Okay, and so on and so forth. Okay, so how are you going to assign the number of math classes offered to this college here? So maybe you would ask if it depends on the number of students enrolled in this department. Okay, let's say department here. So for example, there are let's say 300 students here. Okay, and this one we have let's say 100 students here, and this one is 400 students here, and history we have, let's say 100 students again. Okay, and so on and so forth. So how many math classes are you going to offer to every department? Okay, so notice that the denominator, this one here, is not limited only to the number of people, okay, in a population. So for this one here, let's try this color here. For example, we have a city, we have Valencia City here, Valencia City, and then there are many barangays. Okay, let's say Poblacion, and what do you call this one, example Muswan, if Muswan is part of Valencia. Okay, let's say Dulugon, and so on and so forth. Okay, so suppose that there are, let's say 10,000 people here, and here in Muswan we have 500 only, in Dulugon we have, let's say 1,000 at one, and so on and so forth. So how are you going to distribute fire stations in the Valencia city? So if there are, for example, there are 50 fire stations that the Valencia city had, and then how are you going to distribute those fire stations in these barangays? Okay, so maybe there must be more fire stations in the Poblacion, since there are more people here than the Muswan, okay, or in Dulugon. Okay, so that's one way to look into the denominator. So get the standard divisor and then get the standard quota. The standard quota is the subgroup population. Okay, so total population is, for example, this one, you add everything, so that's the total population. The subgroup population is, for population is 1000. Okay, most one we have 500, and then for example this one, and then the standard divisor. So for example, in population we have 10,000 divided by the standard divisor that you are going to get here. Okay, so anyway, this is the method that you are going to use. The important thing here is that this letter C, okay, this one here, if the sum, let's say another color here, this one, if the sum of the lower quotas is less than the total number of seats to be apportioned, this one here, let's try to use the mouse. If the sum of the lower quotas is less than the total number of seats to be apportioned, then they assign a seat to be the subgroup that has the highest decimal part. This one, this is important, highest decimal part. Okay, this one here. Okay, and then you are going to repeat step C. You will only use this one, C and D, if the total number of representatives, or the denominator, this one, the denominator of the is D, or the standard divisor, if the total number of seats to be apportioned is not reached, then all you have to do is to use letter C. Okay, get the highest decimal part and then add 1. Okay, so for example, let's have this example here. We have Barangay Dulugon with this one. I know that you are familiar with this already. So sum, this is the total population, sum 1250 plus 985 plus 1420 plus 1595, sum it all, the sum is 5250, and then divide by 350, because as you can see here, you are going to apportion 350 sacks, okay, into 4 clusters. We have east, west, south, and north. Okay, and then this is the standard divisor. The quotient is here. So we have, maybe you can use 2 decimal place or 3, it depends. So for standard decimal place that you are going to use, maybe for uniform purposes, maybe we can have 2 decimal place. Okay, so use this one and then use calculator. And then it says in chapter in the step 3 that if you are going to add, okay, what are you going to use here is round down. Okay, in getting the value of the standard quotient, okay, the standard quotient, what are you going to do is use the round down. Okay, not round off. Okay, round down. Okay, so not round off, not round up. Okay, round off, it's the meaning of round off is if you have if the value is below 0.5, then we have round down. If above 0.5, we have round up. So that's round off. So when you say round down, whether it is 83.99, it should be to the lowest integer. Okay, so we have here 83, 65, 94, and 106. So it is round down, and then add the standard quota. Okay, add the standard quota, and then if the result is less than the number of rice to be apportioned, then what you will do is go to step 3. Okay, get the highest decimal part. Okay, so the highest decimal part here is this one. This 2 here, this 2 here, this one, sorry, this one here. Okay, this is the highest, and you only need 2 because you have 350 socks and we have 348 here, so you will only need 2. So as you can see, you have to add 1 here. Okay, 65, it becomes 66. Okay, you add 1 here, 1 plus 1 here. Okay, so the total would be 350 now. Okay, so that's how you are going to use the Hamilton method. But what if, okay, what happen if, for example, this is 349, for example, for example, if this is 349, let's say this is 349. Okay, and there are only 2 quotient here that have the same decimal remainder. Okay, so which one would you choose? Okay, that's the question. All you have to do is to extend this one. Okay, I believe that there's what they call this one, there's more decimal here, digit here, not decimal, digit here. So if the digit after 7 is 5 and after 7 here is 4, then choose this one. The west will win. Okay, but if they have the same for the third decimal, the third place, then go to the fourth place, go to the other, the fifth place, sixth place, and so on and so forth. Okay, so I hope that you have now the idea. Okay, so just be careful. Okay, so I'm going to go back to that one, and the resulting the new table now will be this one. Okay, this table here. So as you can see, we have 66 here. Let's say another color, this one we have 66, and this one is 95. Okay, so this one here, and the total number to be apportioned must be the same, okay, as that of the given. So we have 350. So that's Hamilton plan. Okay, so for the next plan or method, we have the Jefferson plan. So the problem with this method or plan, this is just the same as the Hamilton plan, but the problem is we will be using this so-called modified standard divisor. Okay, modified standard divisor, and finding this divisor is really hard. Okay, this is really hard because you are going to use trial and error. Okay, until as you can see here, let's go back, that standard divisor that you are going to use here, somewhere here, 15 in the Hamilton plan, so you will use less, maybe 14.5 or 13 or 11, and so on and so forth. It depends, as long as if you divide, the resulting sum would be exactly 350. But if not, then choose a standard divisor that will result to exactly 350 sacks to be apportioned. That's really hard if because we are going to use trial and error. Okay, so that's Jefferson plan. So as you can see here in the discussion, I know that you are familiar with this method. So for example, this one, in your module, we use 14.95 instead of 15 as a modified. And by the way, when you say modified, there's something to be modified. Okay, so there's a standard divisor existing, and then you are going to modify it. So that's maybe a little bit funny for me. So anyway, we use here 14.95, and the resulting is table is just the same to Hamilton plan. The result is 348. So make another guess, use 14.92. The second guess is we have here 350. Okay, so but if you are not lucky enough finding the modified standard divisor, then it will take you time. Okay, it will take you time. Anyway, the modified standard divisor is not only one. There may be many modified standard divisor. Okay, it could be 14.93, it could be 14.91, okay, it could be 14.90. Okay, so do not be confused if you try to ask your classmate, to ask for them if you don't have the same modified standard divisor. Okay, some students are lucky enough that if they can choose the modified standard divisor only once, then maybe he or she is lucky enough. Okay, but it should be lower than the standard divisor. Okay, so that's the Jefferson plan. And notice in the what they call this one, the Hamilton and the Jefferson plan example here, they are the same. Okay, the same 83 sacks for the east, 66 sacks for west, and so on and so forth. Hamilton and Jefferson plan, with this example, they are what they call this one, they are the same table. Okay, but there's a note here that I am going to elaborate. It says here that it is not always necessary for the Hamilton plan and the Jefferson plan to yield the same result. Okay, so please be careful here. Let's say this one color here. I'm going to make a box there. Okay, it is not always the result will be the same for the Hamilton and the Jefferson plan. So maybe I can give one example that they have a different table. Okay, so I'm going to pause it now and then come back later to write the example. Okay, this is the promise example that I am going to give you, where the Hamilton plan, the table for the Hamilton plan and the Jefferson plan differs. Okay, so example number 2, suppose the 90 officers, police officers in the province of Bukidnon are selected based on the number of reported crimes per municipality as shown in the table below. So we have here Maramag, Dulugon, Quezon, Valencia, and Malaybalay. So these are the number of reported crimes. Okay, and then you are going to calculate, okay, the using Hamilton plan to determine the number of police officers each municipality should have, and also for the Jefferson plan. Okay, so this is the solution. Remember that the number of let's have another color here. Let's try this blue black one. The number of police, okay, officers to be apportioned is equal to 90. Okay, as you can see here, this one here, 90 police officers, and then First is we are going to calculate the what do you call that, standard divisor. Okay, so SD is this one. This is the total number of reported crimes. Okay, and the denominator is the number of police officers to be apportioned. Okay, so if you try to total the number of crimes, is the value here is, sorry, total, the number the total here is 40,000. Okay, 40,000. Okay, just add, use your calculator. So we have 40,000 divided by 90. The value is 444.44. Okay, use 2 decimal place. Okay, and then all you have to do is to make a table. So don't worry, I'm going to fast forward this one. Okay, this one here we have municipality. Okay, and this one is the number of reported crimes. Okay, and here we have the quotient, and then this one here is the standard quota. Okay, SQ, and finally here is the number of police. Okay, number of police officers. Okay, so from here we have 14,000, sorry, 40 divided by 444.44. Then here we have 4860 divided by 444.44. 3080 divided by 444.4, and then 7440, we have 444.44, and then last one over 444.44. Okay, so use your call this one calculator. The resulting quotient, which will be rounded to 3 decimal place, we have here 31.590. Here is 10.935. This row here we have 6.930, and then 16.740, and then we have 23.805. Okay, so the standard quotient will be using round down. Okay, this is 31, 10, and 6, we have 16, and then we have 23. Okay, see, so the total value here is say this red one, we have 86. Okay, so 86, and we are short to 4 police officers. since our number of police officers is, as you can see here, is 90. Okay, so we have 86, 90, so we are short by 4. So what we do here is we will look at the highest decimal. Okay, the highest decimal in this the quotient column. We have this one. I think this is 935. This one here. Okay, 9393, and this one also. Okay, and this one. Okay, we have 4. So you have to add 1 to the standard quotient. So what will happen here is that we will have 11 here. Okay, is that the, that's not nice. Let's try this black color. We have 11, 7, 17, and 24, and this remains to 31. Okay, 31. So from here we have the total number is 90. Okay, that's 90. So let's try the Jefferson plan. So what I did is I will have the modified standard divisor. I choose for how many values. I choose 438. Okay, so the modified standard divisor is 438. Okay, so I try this one. Maybe you have another, but I'm going to give you later the range of the modified standard divisor. So as I've said, there are many modified standard divisor. Okay, not just only one. So again, get the quotient, and you will get this one. Okay, 438, 4860 divided by 438, 3080 divided by 438. We have 7440 divided by 48, and then 10580 divided by 438. The resulting value is this one, rounded off to 3 decimal place, 32.055, and then this one is 11.096. We have 7.032, and then 16.987, and the last one is 24.155. Okay, so again, round down. You will have 32 here, 11, 7, 16, and 24. Okay, so the total is 90. We have here 90. Okay, we have here 17, so 17, so it's just, this is 31, this makes 32 here. Okay, so we have 90. Okay, so it was notice that the Valencia will be decreased to 16. Okay, and for the Maramag, it moves up to 32. Okay, as you can see here. So there's really a difference between the Hamilton and Jefferson plan in this example. Okay, so notice, I'm going to give a remark here. Before that, before that. Okay, the range for the let's put a note here, note somewhere, this one. The range for the modified standard divisor is, when I played some numbers, this is between 437.64 MSD to 440. Okay, you can choose between these numbers, and the resulting value here is the same. Okay, so I hope that when you try to substitute on your own, then you can get the same answers here. Okay, using example, if you have 439 or 439.5. Okay, and if you try lower than 437.64, then it will not add up to 90. Okay, the goal for the Jefferson plan is it should be equal to 90. Okay, so for this example, of course, so let's have a note here. Okay, let's have a note, remark. Let's say a remark, not a note, remark. Okay, the table, this one, the table below summarizes the number of police officers each municipality should have would have. Okay, would have if the police officers of 90 and let's say 91 members. Okay, the table summarizes the number of police officers each municipality would have if the police officers of 90 and 91 members. Okay, so I played when I tried to add one more. Okay, so when I try to add one more police officers, let's say for example the province of Bukidnon wants to add one more officers, and as you have noticed, this table, which I want to fast forward this later. Okay, I'm going to fast forward this one here. Let's say, let's try to write here, we have municipality. Okay, and then here is for the Hamilton plan with 90 police officers. Okay, there's a purpose for this one. Okay, this one is Jefferson Hamilton plan also with 91 police officers. Okay, and then let's make a table here somewhere. Let's rewrite again 31 11, 7, and 17, and then 24, and this adds up to 90. Okay, this is the total, so we have 90. But when you are using when the province of Bukidnon plans to add one more police officers, since maybe there's enough budget for them, so to hire one more officer, so the resulting value here is this becomes 32, 11, 7, 16, and 24. Sorry, 24. Okay, and also this adds up to 90. Okay, so how did I get these numbers? Just remember that for this one here, so the standard divisor is 40,000 divided by 91. Okay, so get that value, and then so let's try to calculate. So we have 40,000 divided by 91, so the value is 439.56. Okay, so get the quotient, and then if possible you have to add something. Okay, but this is the computation, this one here, this one. Okay, so 30, you will add a value in the Maramag municipality. This becomes 32, so we have here. Okay, so this is 31, so 31 plus this one is 89, so add something here because this one is the have the highest decimal. Okay, this one here. Okay, so in the that this one. Okay, so this becomes 32. Okay, the resulting total number of police officers is 90. So what's the meaning of this? Okay, notice that in this portion here, this one, okay, when there are 90 police officers, the assign the apportion number of police officers assigned to Maramag is 31. Okay, when there are 90 police officers. For Dologon we have 11, here 31, 11, 7, 17, and 24. But when the province of Bukidnon plan to add one more police officer, sorry, Marama gain 1, but Valencia loses 1. Okay, so what will happen? This kind of scenario is what we call the Alabama paradox. Okay, this is what we call the Alabama paradox. So let me put it here, somewhere here. This one, red one. Note that although one more police officers was added, okay, Valencia lost a police officer. Okay, even though the population, no, not population, the number of reported crimes uh, did not change. Okay, did not change. Okay, so I guess this is what we called, this is called uh, let's try this color, Alabama paradox. Okay, so the question here is, since this is not fair, because Valencia loses one more police officer, this result to the discussion about fairness. Okay, we will have a topic with regards to fairness and apportionment, and there are four criteria that I am going to discuss uh, with regards to the topic about fairness and apportionment. Okay, but before that, let me continue to discuss the other two um, methods or plan, the Webster and the Huntington-Hill apportionment plan. Okay, so please remember with this discussion. Okay, I'm going to go back this later. Okay. Okay, this is the third method. We have Webster plan. I intend to discuss the Huntington Hill method as our last topic, because I saw that this method here is lengthy. Okay, anyway, uh, the Webster plan or method is similar to Jefferson plan. Okay, this is similar to Jefferson plan. uh, all you have to do here is that the quotas or the standard quotas will be rounded up. Okay, when the decimal remainder is 0.5 or greater. Okay, so if the decimal remainder is 0.5 or greater, so you have to round it up. And if the quotas uh, where the decimal remainder is less than 0.5, then all you have to do is you will use the this one, rounded down. Okay, and this method here, rounding up or rounding down, is called the rounding to the nearest integer. Okay, this one, this is very familiar in your high school. Okay, so if it is greater than 0.5, you will have to round it up. If it is less than, you have rounded down. Okay, so let me recall that in the Hamilton method you are always be using rounded down. Okay, and also the same is true for the Jefferson plan. Okay, rounded down. Okay, but in the Jefferson plan, you know that you have to get the modified standard divisor. Okay, so here let's have an example. Let's have an example here. Okay, example, uh, consider consider example number 2 using the Webster plan, plan or method. Okay, so this is the solution. Okay, first is we have to make a table. So when you say that the Webster plan is the same as in the Jefferson plan, then we know that in Jefferson plan we have to get the modified standard divisor first. Okay, so in here we are going to get first the modified standard divisor. So MSD, so modified standard divisor. Okay, in the Jefferson plan, the modified standard divisor is less than the, what they call this one, less than the standard divisor. Okay, but in the Webster plan, the modified standard divisor is greater than the standard divisor. So let me put a note somewhere here, maybe this one, note. Okay, in the Hamilton plan, the modified standard divisor for the Hamilton plan, which is MST sub H, is less than the standard divisor. And the using the, what they call this one, the Webster plan, Webster plan is greater than, okay, Webster. Sorry, this is the Jefferson plan. Okay, so please remember this inequality. Okay, when you are using Jefferson plan, it must be less than the standard divisor. But if you are using the Webster plan, you are it must be that the modified standard divisor must be greater than the standard divisor. Okay, so recall let's try to write here. Recall that let's write it here, the ST is 444.44. Okay, and in the modified divisor for standard divisor for the Jefferson plan is I guess between 437, right? 437.64, this one here, MST to 440. Okay, so please recall this one. So I'm going to pass forward by making a table first. Okay, so let's have this one, municipality, municipality, what happened, municipality, and then number of number of what they call this one, number of reported crimes. Okay, reported crimes. Okay, so okay, I am done with making the table. So in here I've tested that the modified standard divisor, it must be greater than 444.44. So I tried 448. Okay, I tried 448, and this is the resulting quotient. So we have 14,040 divided by 448, 4,860, we have 448, 3,080, 448, 7440, 448, and then 10, 580, 448. Okay, so where's my calculator? In here. So let's try 14,040 divided by 448. So this is 31.339. 4860 divided by 448. So we have 10.848. 3080 divided by 448, so we have 6.875, and then 7440 divided by 448 is 16,000, not 16,000, 16.607, and then 10,580 divided by 448 is, the result is 23.616. Okay, so this is the value. So what are we going to do here now is look at the decimal remainder. If it is greater than 0.5, so we will be greater than or equal to 0.5, we will be rounding up, and if it is less than 0.5, we have rounded down. Okay, so here we have 339, is this is less than 0.5, so this is 31. Okay, this is greater than 0.5, we have this is 11. This is greater than 875, 0.875 is greater than 0.5, so we have 7. 6.607 is greater than 0.5, so we have 17. 23 point, we have 616.616 is greater than 0.5, so this is 24. Okay, so adding that up, we have 31 plus 11 plus 7 plus 17 plus 24, the result is 90. Okay, so this is 90. Okay, total. So our modified standard divisor is 448. So what I did before is a note here. This is just a conjecture. I did not prove this one. I noticed that the standard divisor for this is the Hamilton plan. Okay, standard divisor for the Hamilton plan is greater than the modified divisor for the Jefferson plan, and it is greater than the Webster plan. Okay, so, and what also I notice here that the MSD, or the modified standard divisor for the Webster plan, is between something like this one, 445.8. Modified standard divisor for the Webster plan between 445.8 to 450. This is what I notice. Okay, you can try 449, 449.5, and you get the same result. Okay, so if you compare the our previous answer in example 2, the what they call this one, I think they have the same in the Hamilton plan, the Webster plan, they have the same apportion number of police officers. We have 31, 11, 7, 17, and 24. But in the Jefferson Plan, we have 32 here, 11, 7, 16, and 24. Okay, so there is a difference between Jefferson Plan and Webster. Okay, but the Hamilton and the Webster Plan in this example are the same. Okay, this is how you are going to apportion using the Webster method. Okay, so for our next topic, which is the last method, will be the Huntington-Hill method. Okay, so I'm going to pause it for now and then come back later. Okay, this is now the last method, the Huntington-Hill apportionment method. Okay, so what has been given to you in the module that was uploaded in the Google Classroom is that this method here that was presented is not the correct one. Why is that? Because the Huntington-Hill apportionment method has a procedure just like the Hamilton plan and the Jefferson plan and the Webster plan. So in here, let me explain this what has been given to you in the module is that the problem here is you are given a table where it was calculated that the representative was already given. Okay, so it was already given the representative, meaning to say that the problem was already solved by Hamilton plan or Jefferson plan, and then you are asked to ask you are asked to add one more what do you call this one, and one more representative, or in this problem here, one new sack of rice to be apportioned. Which of the cluster, four cluster will receive the what you call that, the new sack of rice. So as you can see here, what you did is you use the Huntington-Hill apportionment principle, and this is related to the what they call that the topic, relative unfairness of the apportionment, meaning to say it was already discussed that the fairness of apportionment topic. Okay, this principle here will be discussed later after the discussion of the fairness of the apportionment. uh, Fairness of the apportionment. Okay, this is under this topic, that topic, the Huntington-Hill apportionment principle. So the Huntington-Hill method is something different than the Huntington-Hill apportionment principle. Okay, because this is that method is the same as Hamilton and Jefferson and Webster. There is a procedure that you are going to follow in order to on how to apportion the number of representatives. Okay, so anyway, this is not the correct one. I'm going to write it here. This is the what do you call this one, the Huntington-Hill method, or HHP or HHM. So this is the procedure. First is you have to get the standard divisor, the same as that of the Hamilton plan, and then get the standard quotient, which is also the same as that of the Hamilton plan. And then in step 3, procedure number 3 is you are going to round down, sorry, this is round down round down the standard quotient and call it the lower quota. Okay, so what you get in the standard quotient, the quotient, you are going to uh, call it is a lower quota, and that lower quota will be denoted by n. Okay, and then you are going to compute the geometric mean, which is equal to this formula here, square root of n times n plus 1. This is your n is the lower quota. And what you will do here is, if the quota is larger than the geometric mean, then you are going to round up the quota. If the quota is smaller than the geometric mean, you are going to round down the quota. Okay, and then after that, you are going to add up the resulting whole numbers to get the initial allocation. If it is equal to the number of representatives, then you are going to stop. If it is not, then you have to uh, go to step number E, or the procedure letter E. So in here, in procedure letter E, it says there that if the total from step D was less than the total number of representatives, you are going to reduce the divisor. Okay, and recalculate again the quota and allocation. So meaning to say that uh, in step 4, if it is less than 90 in our previous example, then you are going to reduce the divisor. If the total was larger than the total number of representatives, meaning if it is 91, 92, or 93, and all you have to do is to increase the divisor. Okay, and then recalculate again. Continue doing this until the step 4 is equal to the total number of representatives. In our previous example, if it is 90 already, then you are going to stop. And that divisor now is what we call the modified standard divisor. This one. For modified standard divisor for this one here, for the Huntington-Hill method. Okay, or other term for that is the adjusted divisor. Okay, so I hope that you catch up or you get the idea on how to use the Huntington-Hill method. So let's have an example here. I've write it already, the table. You have here the same example number 2 using the HHP. Okay, by the way, the what they call this one, the Huntington-Hill plan is the modification. This is a modification of Webster plan. Sorry, this is a modification of Webster plan. The what they call this one, the Jefferson the Webster plan is the modification of the Jefferson plan. Okay, so I hope that you are listing that note. Okay, idea. Okay, modification of Webster plan, the Huntington-Hill plan. And again, the Webster plan is the modification of the Jefferson plan. Okay, and the Jefferson plan is the modification of the Huntington the Hamilton plan. Okay, so let's have now the example. So maybe let's move up somewhere here. So as before, where's that one? As before, if we use the standard divisor here, this quota here, we use the standard divisor to be 400 44.44. Okay, let's try that one. And we know that the value here is 31.590, and here we have 10.935. Just recall your solution in example number 2. So 6.930, 16.740, and this is 23.805. Okay, so what are you going to do here is, it's said in step C that you are going to get the lower quota, round down. So just like the Hamilton plan, you are going to round down this. This is 31, 10, 6, and 16, and then 23. So to calculate the geometric mean, you have to substitute. This is your n. Okay, this is your n. So this is n times n plus 1. Okay, so what happened here is 31 here, you substitute square root of 31 times 32. Okay, then the answer is 31.496. Okay, then again 31, this one here, 31 times 32, we have 10 times 11, 6 times 7, 16 times 17, take the square root, 23 times 24, take the square root, and then you will get this value here. We have 10.488, 6.481, and then 16.492, and then 23.495. Okay, so what are you going to do now is to compare the standard quota and the geometric mean. It says here that if the quota is larger than the geometric mean, round up. Okay, the quota. If the quota is smaller than the geometric mean, smaller, as you can see here, larger and smaller, then we have round down for smaller, round up for larger. So let's look at here. Let's have this color, maybe this one, color purple or magenta. So we have, this is greater, as you can see, this one, compare this one. Okay, so greater, 31, greater, this is greater, that one, compare. Okay, this is greater again, that one, 16.74, we have, this is greater, 23.805 is greater, that one. So what are you going to do? This is 32. It says that round, you are going to round up. Okay, 32, 11, 7, 17, and 24. So the initial value here is how much? That one, 32. I have a calculator here. 32 plus 11 plus 7 plus 17 plus 24. So the result is 91. Okay, the value here is 91. Okay, so it says here that in step E, we have the step E, if the total is was less, this is not less than, we have 91 is greater than 90. Okay, the number of representative, the no, not the number, the number of what do you call this one, the reported crimes. Okay, reported crimes, no, not the reported crimes, I guess that's the number of police, sorry, number of police officer to be apportioned. Okay, apportion is equal to 90. Okay, so we have greater, so we go to the second sentence, I guess this one. If the total from the step D was larger than the total number of representatives, you have to increase the divisor. So instead of 444.44, our modified divisor will be greater than this one. Okay, so we are going to use maybe 445, 446, 447, and so on and so forth, and then test again. Okay, so that would be very a long way to go for you to calculate again and again until you get the number of police officer to be apportioned. Okay, but I've already solved this one. What I've noticed is that the modified, let's say this color black here, the modified standard divisor for Huntington-Hill method, okay, that one is between uh, this is between 446 and 451. Okay, 451. Okay, that's how you are going to get the modified standard divisor for the Huntington-Hill apportionment principle. Okay, so here let me choose let's say let's choose for example, which is what if 450? Let's try 450. Okay, so and then recalculate again. Okay, so I'm going to erase this one first and then come back later. Okay, so we just wait. Okay, let us now compute the standard quotient. So what are you going to do is modify the standard divisor is 450. So 14,040 divided by 450 and so on and so forth, 4860 divided by 450 and so on, and then you will get a value from here. So I calculated already this value, and these values are here. Okay, that one. So let's paste that one. 31.2, 10.8, 31.2 00, 10.800, and then 6.844, 6.844, and then 16.53, 16.533, and then finally we have 23.511, 23.511. Okay, so in step 3 we have round down here. This is 31, 10, 6, 16, and we have 23, and this is your n. So plug into the geometric mean formula. So square root of 31 times 32, this is the same as before. So the value is 31.496, 10.488, 6.481, 16 point, sorry, this is 492, and then 23.495. Okay, so compare the quota, standard quota, and the GM. Okay, so this is less than this one here, this one, compare 10.8, we have greater, this is greater, this is greater again, and this is greater again. Okay, so it says in the step D. Okay, if it is less than, then you have to round down. So this is 31, this is 11, this is 7, this is 16, 17, and this is 24. Okay, so sum it up, and then we have 31 plus 11 plus 7 plus 17 plus 24, we have 90. Okay, so the total is 90. Okay, so that's how you are going to use or to follow the procedure of the Huntington-Hill method. Okay, so this is the modified I already told you a while ago that this is a modification of the Webster method, and the Webster method is the modification of the Jefferson method, and again Jefferson method is the modification of the Hamilton method. Okay, so you can try values between this uh, inequality here, 446 and 451. Just try 449. If you want to try higher than this, it's let's say 452, then you will notice that uh, it will become smaller. Okay, smaller than 90. Okay, so just play, use your time to what they call this one, to analyze this example. Okay, so I think we are done with the apportionment method. Okay, let's now talk about the what they call this one, the fairness. And as I've told you in our previous example, let me go back to that example. Somewhere here, I guess this one. Okay, we will be talking about the paradox. Okay, so we notice that this example, our example number 2, commits or violates the Alabama paradox when you are using the Hamilton plan. Okay, when you are using the Hamilton plan. Okay, so let me elaborate here that where's that one, this one here, that there should be a fairness criteria in order for the what they call this one, the method of apportionment that you are going to use will not violate to that given paradox. So Alabama paradox is something like, if you are going to increase the number of representatives, and if the given states, or somewhere here, this one here, or this municipality, if he loses representative with that of the original one before adding a new representative, then the it said that plan commits the Alabama paradox. Okay, there are other paradox that was listed in your module. The I think, if I remember, the new state paradox and the population paradox. So I'm going to paste it here and then discuss that one. Okay, just wait. Okay, these are now the three paradox that I've mentioned before. The three paradox: Alabama, population, and the new state paradox. So actually we cannot discuss the fairness and apportionment if we don't have an idea of what an apportionment paradox is. Okay, so as I've discussed earlier in the previous example, which is example number 2, when we use the what they call this one, the Hamilton plan, it violates the Alabama paradox. Okay, so the question now is we what are we going to do in order for what they call this one, for the method that we are going to use will not be able to commit violates the said paradox. Okay, so we will be discussing later about the fairness and apportionment. Okay, so as you can see here, Alabama paradox is this one. If you are going to increase the total number of items to be apportioned, so when you say total number of items to be apportioned, this is the same as the number of people to be apportioned. Okay, but as I've discussed before, this the apportionment method is not limited to the population of people. Okay, you can have like this one. Okay, total number of items. So if you are going to increase, then if a particular state will lose an item for a group, or lose an item for a given state, then that then we commit the Alabama paradox. Okay, in the population paradox, if you are going to increase the population, in the Alabama the population is the same, but if you increase the population and the number of representatives or the items is the same, and what will happen if someone is lost again an item, then you commit the population paradox. So the difference between Alabama and population is that the Alabama is you increase the total number, the number of items to be apportioned, but here in the population is if you increase the total population. Okay, the population of a group. Of course, if you increase the population of a group, then the total population also will increase, or if it will decrease, then it will decrease also. Okay, so that's the difference between population and Alabama paradox. The new states paradox is similar. Just look at the keyword here. This one, when you say new states, if you are going to increase the states, example, if there are 5 states, or just like in our previous example, we have municipality, there are 5 municipality. If we increase the municipality to 6 municipalities or 7 municipalities, if someone loses, then that apportionment method commits or violates the uh, new states paradox. Okay, so that's the difference between these three. Okay, Alabama, population, and new states paradox. Okay, so before I am going to discuss the Balensky-Young impossibility theorem, let me discuss first the fairness in apportionment, which will come after this. Okay, okay, this is the question. I write it here. Although the average constituency of the Jurassic Park and College Park are approximately equal, which park has the more favorable representation? Okay, so I guess this is a question mark, not one. So the answer would be what? So remember that if you have a smaller average constituency, this means that for every representative here, this one here, for every representative here, one representative, he will serve 1,600 people. Okay, so it seems like the more favorable here is the smaller average constituency. Okay, smaller. So like this one here, we have one. There are for every one representative, he will serve 1,668 people. Okay, the smaller one is the answer. Okay, so the answer is Jurassic Park. Okay, Jurassic Park. Okay, so another criteria that we are going to use is the absolute unfairness of apportionment. So how are you going to use this criteria? So suppose, for example, that one representative will be added to one of the parks, okay, in Jurassic Park or in the College Park, one representative, okay. And then the question is which park is more deserving of the new representative, okay. So which park is deserving, okay. So in other words, to be fair, which park should receive the new representative. Okay, so as you can see here, this is the table, this is the formula. The absolute unfairness apportionment, or AUA, is the first is you have to get the average constituency of A, and then get the difference, and then get the absolute value. Okay, so from here, for example, we have, if you are going to add, so put in the upper part here, we have Jurassic Park, average constituency. Then the College Park, we have average constituency here. Then this one here on the left hand side, we have to receive the new representative. Then the College Park also. So we have, before we have 10, so plus 1 we have 11. So this one is remain 1,600 divided by 10. Okay, and this one here, we have 8,340 divided by 5 remain, and then this one here is we have plus 1. Okay, the resulting value, we have to get the difference between, doesn't matter if 1455 is placed first than College Park here. All you have to do is to get the absolute value. Okay, so 213 here and also 210 here. So the answer is, if you have a smaller absolute fairness apportionment, and if that occurs in the College Park, then that park will receive the new representative. Okay, so from this we have the smaller, which is 210, as you can see here. Okay, as you can see here, that one. Okay, so smaller in the average constituency is smaller. Okay, so the question now is there's a last criteria, which is the relative unfairness of an apportionment. Again, you cannot get the relative unfairness without the absolute unfairness, and you cannot get the absolute unfairness if you don't have the average constituency. So be careful that you memorize the formula. Okay, so this is the formula. Average and this one is AUE, is absolute unfairness of apportionment, and then get the AC of the subgroup receiving the new representative. Okay, so from here, so make this table. So the formula is this one. So the relative unfairness of the Jurassic Park is AUA. This one, AUA, is 213. This one of the Jurassic Park here, we have 213 divided by AC, average constituency of the subgroup receiving the new representative. Okay, new representative we have here. We have plus 1 here, plus 1. Okay, so we have 1455. So 0.146, and for the College Park we have 0.51. So the conclusion here is that if the what we call this one, this idea here will be used in the apportionment principle. It says here that when adding, this is for adding a new representative to a subgroup, the reverse representative is assigned to the subgroup in such a way as to give the smallest relative unfairness of apportionment. So from here, since 0.146 is smaller than 0.151, the park that will receive the new representative is the Jurassic Park. Okay, so Jurassic Park will receive the new representative. So from the previous example, we have here Jurassic Park is approximately 0.141, while the College Park is 0.151. By the apportionment principle, we will be the park that will receive the new representative is the Jurassic Park. Okay, so I hope that you are familiar now with this fairness criteria. And notice that in this example, there are only two states that we consider. But what happens if you have 3 states or 4 states or 5 states? So it will increase the number of computation. Okay, so just get the pairing. Okay, for example, if you have, let's say, we have here Jurassic Park, and then College Park, what kind of park, Sunshine Park, what other, let's say, no park, no parking, something, say, anyway, just compute the how many computations. So I guess compute this one, JP and CP, then compute JP and SP, and then JP and NP, then compute CP SP, then compute CP NP, and then finally compute SP NP. So meaning to say, you are going to get a how many computations. I think there are 4 taken 2 computations, which is, this is familiar in your statistics. This is 4 factorial divided by, and this, the formula is this one, CR. We have n factorial divided by r times n minus r factorial. So this is 2 factorial times 2 factorial, which is 6 ways or 6 computations. Okay, all in all. Then the smaller relative unfairness of apportionment will receive the new representative. Okay, that's really a hard, not hard, but it takes you time to compute 6 ways. What if there are 10 states here or parks here? We have 10 taken 2, that's a lot. I guess the computation shows that when you have 10 taken 2, where's that one? We have 45 computations. Then that's a lot. Okay, so what are we going to do here? Luckily, not luckily, but there's a way. We will be using the so-called, in our previous example here, the Huntington-Hill number. Okay, this one. So I guess where's that one? Let me where's that one? Okay, I cannot find it. This one. Okay, this is how you are going to compute the no, not that one. This is how you are going to compute the relative unfairness of apportionment. Instead of using that one, there is a shortcut, which is what we call the Huntington-Hill apportionment principle, and we will use the Huntington-Hill number. Okay, this one. Okay, if you are going to this method here is if you are going to add one representative. Okay, this one. Add one representative to a number of subgroups, only one. All you have to do is instead of computing the relative unfairness, you are going to compute the Huntington-Hill number. Okay, so this one PA is the population of the subgroup A, and we have our A here is the current number of representatives of a subgroup. So meaning to say, there's already a representatives in the given group. Okay, so for example, in the what they call this one, in the previous example, instead of computing the Huntington-Hill number, no, the relative unfairness, just use this one. Okay, example here, the Huntington-Hill number of the college, the Jurassic Park. Okay, that one. So the answer is, I guess this is 10. Okay, population. No, this is not a population. Population is, I guess, 16,000. If I remember it correctly, we have 16,000. Okay, you have to square that one based on the formula here. And then the current representative, number of representative that was assigned in the College Park is 10. So we have 10 times 11. Okay, compute that one. For the College Park, we have I forgot, sorry, I forgot, maybe that's 8,340. Okay, 8,340 square, and then it was assigned by 5, so 5 times 6. So calculate that number. So we have 16,000 square divided by 10 times 11. Okay, so the answer is 2,327,272. Okay, 0.727. And then this one is 8,340 square divided by 5 times 6. We have 2,318,520. Okay, so as you can see here in the Huntington-Hill apportionment principle, says that the representative should be added to the subgroup with the greatest. Okay, greatest. All of them are smallest. Average constituency is smallest. The AUC or ACU is smallest. The RUA is also smallest. So from here, in the Huntington-Hill apportionment principle, we will use greatest. Okay, so which one is the greatest? Okay, I think this one. Okay, let's have another color here, this one. Okay, and we are correct. Okay, the new representative should be assigned to the Jurassic Park. Okay, notice that they have the same, the computation is only 2 computations, but if the number of state is increased, then for example this one, this example, our previous example, we have 4 taking 2, we have 6 computations, but here we have 4 computations only, so it will shorten the time. Okay, so based on this computation, the highest is 224.30. So this one, the North will receive 1 new sack of rice. Okay, and I've discussed this earlier. The other applications, just read that one. This is equivalent to the discussion before when I say that the number of people to apportion is replaced by this situation. Okay. Okay, so I guess we are done with the discussion of the, what do you call this one, discussion of the fairness in apportionment, and I guess we are now ready to discuss the Balensky-Young, this one. Okay, Balensky-Young impossibility theorem. Okay, so just wait for a moment. Okay, we are now going to discuss the Balensky-Young impossibility theorem, this one here. Okay, what does this mean? This means that in any given apportionment method, either it will violate the quota rule or will produce paradox such as Alabama paradox, okay, or the new state paradox, or the what they call this one, population paradox. Okay, please do remember that there's no perfect apportionment method. This theorem says that there is no perfect apportionment method. Okay, so this is the what they call this one, this is the summary of the uh, plan that we've used. Okay, so as you can see here, Hamilton plan will not violate the quota rule, as you can see here. Okay, but Jefferson and Huntington-Hill and also the Webster, I'm going to put it here, let's say this color red here, Webster, okay, it may violate. Okay, but it will not commit an Alabama paradox. Okay, cannot occur something, cannot occur. Okay, so meaning to say that Hamilton plan, as you can see here, it will violate the Alabama paradox, population, and new state paradox, while Jefferson, Huntington-Hill, and Webster cannot. But for the quota rule, only the Hamilton cannot violate, but Jefferson, Webster, and Huntington-Hill will violate the quota rule. Okay, so just remember, the Balensky-Young impossibility theorem says that there's no perfect apportionment method. Okay, so before I will end and move to the second part, which is the voting, let me give you a warning here about this fairness, absolute unfairness. It says here that when, if you have the smaller, this one here, absolute unfairness of apportionment, this one, okay, this one here, then the one that will receive the new representative will be the this one, the smaller one. Okay, this one here. Okay, in this example, but this is not always the case. Okay, this is not always the case that you will consider the smaller absolute fairness of apportionment. It depends upon the example. Okay, so let's have an example here where, for example, this one, let's have an example here about AUA. Okay, average what do you call this one, average unfairness of apportionment. Okay, so maybe we have to wait for the program to respond. Not average, absolute. Okay, absolute unfairness of apportionment. So for example, you are going to invest a money to a particular product. For example, you are going to invest 1,000, for example, 10,000 pesos. Okay, you have investment A, and investment B here. Suppose that you are going to invest 10,000 pesos for investment A for a particular product, and then investment B, which is let's say $20,000, no, pesos. Okay, so this is the original investment, original investment. Okay, and then after 1 year, okay, 1 year later, sample this one, the 10,000 pesos becomes 11,000 pesos after 1 year, and then the 20,000 pesos becomes 21,000 pesos, 21,500 pesos after 1 year. So the increase, as you can see here, is 1,000. Okay, and the increase here is 1,500 after 1 year. Okay, so if you are going to what do you call this one, if you are going to use the average, the absolute unfairness of apportionment, okay, let's calculate here, for example. Okay, just wait, I'm going to put a line here, something. Okay, I already make a table, put already a line here. So the question for this problem is how to analyze the absolute unfairness of apportionment. So the question for this problem is that please to remember that the investment for A is 10,000 and for B is 20,000, and 1 year later we have this one, and this is the increase. Okay, so which is more productive for this investment? So as you can see, we did not already compute the we did not compute the average constituency. So the table is fixed, so it's just like saying that 11,000 minus 10,000 is 1,000, and we have 20,000 minus 21,000 is, take the absolute value, we have 1,500. Okay, so the question is which is more productive in this case. Okay, it seems like, as you can see, the investment B produce larger profit. Okay, we have 1,500 than investment A, but as you can see here, the investment which is more productive is, I think, investment A. Why? Because as you have noticed, if you divide 1,000 by 10,000, so for investment A, if you divide 1,000 divided by 10,000, you will get 0.1. Okay, and for B, if you have 1,500 divided by 20,000, you will get 0.75 cents. Okay, this means that for every 1 peso, you will receive 0.1 cents, and here for every 1 peso you have 0.075 cents. Okay, so for this, in this scenario, in this scenario, in this scenario, investment A uh, was more productive. Okay, productive. Okay, so be careful in analyzing how to use the absolute unfairness of apportionment. It depends upon the question. Okay, so I guess that's all. I guess we are now ready to go to part 2. Okay, but before that, if you are new to this lecture, please subscribe to my channel. Just click that subscribe button and bell button down below for instant notification. God bless everyone. Okay, I'm sorry I have to include this historical note here. I forgot to discuss this after the discussion of the what they call this one, the Huntington-Hill apportionment method. And also I reminded myself about the difference between apportionment principle and Huntington-Hill apportionment principle. Okay, the Huntington-Hill apportionment principle, that principle depends on the Huntington-Hill number. Okay, while the apportionment principle, uh, that one depends on the relative unfairness of apportionment. So be just review your definition that was uploaded in the Google Classroom in your module, or maybe in this discussion. uh, just recall that the topic. Okay, so there's a difference between Huntington-Hill apportionment principle and apportionment principle. Okay, so for this last one here, we have this historical note. It says here that according to the U.S. Bureau of Census, methods of apportioning the House of Representatives have changed over time. So in 1790 to 1830, they used Jefferson method. 1840, we have Webster. From 1850 to 1900, we have Hamilton method. 1910, they used to 1930, and 1930 they used Webster. And what else? 1940 to 2010 is the method of equal proportions, or the Huntington-Hill method. I don't know uh, the latest from 2011 to 2020 what method they use. Okay, so maybe I guess there's a law also in the US where, and every 10 years they have to do again the census. Okay, and I guess as of this year, there are, I guess, 300 more than 308 million Americans uh, in total, for the population of the Americans or the United States. It's more than 308 million. Okay, it says here also this portion here. Let's have this color. This one. This one here. This one. It says here that all apportionment plans enacted by the House have created controversy. Okay, there's always a controversy with regards to those for apportionment method. So it says here, for instance, the constitutionality of the Huntington-Hill method was challenged by Montana in 1992 because it lost a seat to Washington after the 1990 census. Okay. However, if I remember it correctly, there's a precedent where he chose that particular apportionment method because for him it would benefit to his hometown. Okay, it will add one more representative. Okay, so anyway, that's depends on the current what do you call this one, administrator. Okay, so I guess that's all. So please do recall or review your notes with regards to the apportionment principle and the Huntington-Hill apportionment principle. There's a difference between those two.